In this video, we are going to talk about the continuity of a function. The easy way to test if a function is continuous or not, you just see if you graph a function, you lift your pencil or not. If you don't lift your pencil in order to draw a graph, then that is continuous. So several examples that not continuous is there is a hole. So when you draw it, you need to lift your pencil in order to go the other side of the function. So, but this type of continuity, we call it removable. And the jump is from both sides. The function is not approaching to the same limit, so there is a jump. And the gap is you have both function approaches infinity, but they are not continuous at that point. So the last two, they are not removable, this continuity. So the continuity definition is a function is continuous when the limit from both sides equals and exists, but also equals the value of the function at that point. So normally you could use a 3-step to test it. Step 1, you need to see if the function at that point is valid, is defined. If not defined, then we know that is not continuity. And step 2, you need to check if the limit exists at that point. So when x approaches a, f at a exists or not. How to prove it is exists? Then you are going to check the left side and the right side limit exit and equals. So this is not a, but it's x. And step 3 is the limit also need to equal to the function value at x equals a. So f at x equals the value of the function at that point. So instead of if you have the function's value at another point, then that is not continuous, but we call it removable, this continuity. And so this is what we need to know for today, and we are going to apply those conditions, step 1, step 2, step 3, to check if a function is continuous or not. A function is said to be continuous on the interval from x greater than equal to a less than or equal to b is continuous if it is continuous at each point in the interval. So that is definition for continuity for a function. Now we are going to use these 3 steps to determine if each of the following functions are continuous or discontinuous. So the first question is you see if you follow this graph, you don't have to lift your pencil, then this is continuous. This is continuous. At each point, it's continuous. There is no jump, no gap, no break. And for this one, you will see there's a hole. So you go the function from this side, then at hole you need to lift your pencil in order to continue. So this is discontinuous. And how you can say it, you could say that at the hole f at, I think it's f at 1, doesn't exist. So there's no function value at x equals 1. So as long as a function is undefined, then this is not continuous. And for this one, at this point, you will see the function, step 1, function at 1 is defined, equals a number 5 point something. And step 2, the limit at each side, they are limit to the different numbers. So from the left is 4, from the right is 5.2. They are not equal, so the second one, the limit doesn't exist. Limit doesn't exist. Then it is discontinuous. So this is a step 2 we stopped. And the last one, the f at 1 doesn't exist. It's going to the infinity, so it doesn't exist. The limit, we could say it is exist, is equal to the positive infinity. So step 1 doesn't pass, but step 2 passed. So it's still discontinuous. So use this 3 steps to make sure that it passes all the 3 steps. So continue example 2. Find the limits at x equals 1 and x equals 2. So and after that you are going to check if it's continuous at x equals 1 and x equals 2. So limit, we are going to see the left side limit of this function equals, so from left side you will see on the graph the value is approaching to the y value is 3, and from the right side we look at the graph on the right side of the 1, then you will see, you put your pencil on the graph, when x equals 1 the y value is 0, and 3 is not equal to 0, so we know that the limit doesn't exist. Limit when x approaches 1 doesn't exist. So this is for x equals 1, and for x equals 2 we do the same thing. Limit x approaches 2 from the left side. On the graph, we go from the left to x equals 2. It gives you the y value is 2. And we do the same thing from the right side of 2 on the graph. We put our pen here on the graph. When x equals 2, it approaches y value is 2. So 2 equals 2, then limit exists and equals to the left side and the right side limit is 2. And it asks you if the function continues at x equals 1. So x equals 1, you will see f step 1. F at 1 is defined equals 0. It's solid dot. But the limit step 2 doesn't exist. Then it didn't pass step 2, so it stays continuous. And for the x equals 2, we are going to see step 1, f at 2 is defined equals to the solid dot equals 1. And step 2, the limit exists equals 2. And step 3, these two numbers need to be equal in order to continuous. So these two numbers not same, so this function is discontinuous at x equals 2. So remember 3 steps. Step 1, step 2, step 3. If it pass all the 3 steps, then it is continuous. Otherwise, it's discontinuous. So example 3, it is a piecewise function. In each interval, it has a different expressions for this function. So when x is from negative infinity to negative 1, it's negative x squared. We are going to draw the xy axis and draw the graph. So I draw the xy axis and label the scales. Now from negative infinity to negative 1 is negative x squared. So we know x squared is open up, negative x squared is open down. So when x equals negative 1, we sub in is negative 1. So this one not solid not squared bracket, so this one is doesn't include the -1, so it's a whole here. So we put -1 as a whole, then we sub in -2 here. -2 squared give you 4, -4. So -2, -4. Then we connect it. This is a y equals -x squared for this piecewise function, and x equals 1, it gives you the solid dot is +1. Then after that, when greater than x equals -1 to positive infinity is y equals x. Y equals x is our linear equation, so the y-intercept is 0, x plus 0, so it passes y-intercept 0 and use a slope 1 over 1 is your step pattern, is a slope, so right one up 1, right one up 1, you have 2 points. Now at x equals -1, it is -1, and but it's a whole. So now we have this y equals x at this point, and after sketch it, it asks you to find each limit if it exists. If the limit doesn't exist, it explain why. So this one is from left side to the -1. From left side to -1, you will see the y value is approaching -1, so equals -1. And from the right side of -1 is approaching -1. So the limit, right side, left side, they are equal, so it exists, equals -1. And the next question is asking you if the function continues at x equals -1 or not. We use our 3 steps. Step 1, f at -1 is defined is equals to +1. And the second, the limit at x approaches -1 exists, equals -1. Step 3, 1 is not equal to -1, so this is discontinuous. So 3 steps will help you to determine if a function is continuous or not. So this is how you do it. And the next example, example 4. So determine whether each of the functions at x equals 2 continuous or not. If it's not continuous, give a reason why. So this one, x cubed minus x. So this one doesn't have any wholes, doesn't have, it's valid for the whole, all real numbers, so it is continuous. And we don't have give the reasons. If give the reason, you will see the f at 2 is defined. You sub in 2 cubed minus 2 give you 8 minus 2 is 6. And the limit, because it is no x equals 0, no denominator equals 0, so f at x, when x approaches 2, you do the direct substitution, is 6. So step 1, step 2, then 6 equals 6, it continues. The next one, g at x. For g at x, we are going to see step 1. G at 2, we sub in 2 minus 2 give you 0. So divide by 0 is undefined. Then it is discontinuous. We don't have to go further. So it's discontinuous. So the function is undefined. Although the numerator is 0, so as long as the denominator is 0, it's undefined. It doesn't like the limiting value. Limiting value, we could factor it, cancel something out, then we could find the limit. But for the value of the function, we need to do the direct substitution. And h at x, so this one, h at x equals this one. When x is not equal to 2, is this function. When x equals 2, it gives you the 3. So if it's subbing 2 here, it's undefined, but it's have a restriction, x not equal to 2. So this is step 1, h at 2 is defined. And step 2, we are going to find the limit. So limiting value when x approaches 2, h at x equals what? Limiting value x approaches 2, the denominator is 0, so we want to find if we could factor the numerator with this factor. So we may just guess, if we put x minus 2 here, can we find another factor? So this one, first term divided by first term, x squared divided by x, you have no choice, it's x. Last term divided by last term, negative 2 divided by negative 2 is positive 1. And don't forget, you need to check the x term is right or not. So negative 2x plus 1x is negative x, so this factor is correct. Then x minus 2 is a factor, we can cancel it out. Then we have x plus 1 left. We just say one more step. We just cancel these two out. Then we sub in x equals 2. We have 2 plus 1 equals 3. Then we check step 3. The value of the function at x equals 2 is equal to the limit of that function when x approaches 2, so it is continuous. Then we do the same thing for question D. Question D, step 1. F at 2, we sub in 1 over 2 minus 2. Give you 1 divided by 0, undefined. Then we know it is didn't pass the step 1, is discontinuous. A function need to pass all the 3 steps. So for the last question, so step 1, we check the function's value g at 2, this one equals 2, so it will be 3. And step 2, we are going to find the limiting value from the left side and also from the right side. So from the left side, it will be smaller than 2, so we sub in the 2 here. So 4 minus 2 squared give you 4 minus 4 is 0. Then step 3, actually from the right side, it will be 3. So we don't have to go to step 3. The step 2, the limit doesn't exist. Then we can stop here. Doesn't exist. Then we can stop here. It's not continuous, discontinuous. And after that, we want to double check. So for this one, the limit doesn't exist. This one is a jump. Jump, discontinuous, is not removable. And for this one, it's undefined. It's kind of, we have the limit from both sides is infinity, and here is infinity discontinuous, so it's a gap. It's not removable discontinuity. This is not removable. and for this one is continuous, this one undefined is discontinuous, and if we check, we could see that the limit exists. So this one you will see the limit. When x approaches 2, we have x plus 1 then equals 3 is from here. So the limit exists, but there is a break, so this one is a break, is a hole, and this one is removable discontinuity. Okay, this one is removable. So in this lesson, what we have done is use 3 steps: step 1, step 2, step 3, to see if a function is continuous or not. It need to pass all the 3 steps, and if it's a hole, it's a removable discontinuity, and if it's a gap, then it's not removable discontinuity, and if there is a jump, the limit doesn't exist from, they are not same at both sides, it's a jump, it's not removable discontinuity. So thanks for watching.